We are delighted to have with us today Mark de Berg, who is well known for his many contributions to computational geometry and for the Dutch book. You may be able to see behind my back the 3 editions of the Dutch book. I should also say that personally it's a pleasure because we are from the same generation. We more or less grew up together in computational geometry and cooperated throughout the years. Mark will talk about clique-based separators. Mark, please.
Okay, thank you very much, Danny. Yeah, so usually I say it's a pleasure to speak in the seminar. I have to say I hate Zoom seminars, but for such a good friend and old colleague and somebody I grew up with like Danny, I could not say no. So here I am. And I hope that the fact that I hate Zoom seminars doesn't show too much in my presentation. As Danny mentioned, I realized it's the first seminar of the year, so I'm going to try to keep it relatively high level. So it's more like a survey talk, perhaps, than an in-depth talk about one topic. But I hope you like it nevertheless, and I think it's a very nice topic. So yeah. Let's see. So I want to talk about clique-based separators, but first to give you some background, let me start with planar separators and tell you something that hopefully all of you already know. So suppose you have a planar graph, right? So a graph that you can draw without crossing edges. Then there's this very famous theorem originating from Lipton and Tarjan already in the 70s of last century that says that in any such graph, you can find a subset of the nodes called a separator whose size is relatively small, actually only square root of the number of nodes. And if you remove them, the graph splits into components of size at most 2/3 of n. Right, so here the components need not be connected. So it's if you remove S, you can partition the remaining nodes into 2 sets, A and B, such that there are no edges between A and B. And after Lipton and Targent results, there are many other follow-up papers proving better constants in the big O or maybe having some additional properties. But for us today, this is the main thing that we will be looking at. So I guess many of you probably know a number of proofs for the planar separator theorem. There's this layering technique, which was what Lipton and Tarjan originally did. There's some other techniques. There's also a very nice and actually simple geometric proof that I want to show you. And that goes as follows. You know perhaps that any planar graph can be represented as an intersection graph of disks that are touching, right? So here you see, right? So here you see a graph, and here it's represented by every node becomes a disk. The disks don't intersect, or at least their interiors don't intersect, but whenever they touch, there's an edge between them. And there's a famous theorem saying that any planar graph has such a representation. Then you can find a separator in a geometric way by trying to find a square. You could also find a circle, but let's do a square. A square that intersects only few of the disks, only square root of n of them, and that has, let's say, 2/3 of the disks inside at most, and at most 2/3 outside. Actually, the balancing factor is going to be a little bit different than 2/3, but that doesn't really matter. And then, of course, the disks intersecting this square will be the separator, and the other disks will be inside and outside, so they form the 2 sets. So you can prove that such a square exists in a relatively easy manner, and this goes back maybe to Smith-Wormold in 98. There's a paper by Sariel and Kent Conroot where they do the same thing, and the proof is actually very nice, I find. So it works as follows. First, you take the smallest square, that's the blue square you see here, that contains, let's say, n divided by 36 number of disks. Okay, and the 36 is just the number that makes it work or that is easy to do. Now, the idea is that if you blow up this blue square by a factor of 3, you get the outermost red square. In between, I'm going to put square root of n other squares, like the red ones you see here, at equal distance from each other. Right, so let's assume maybe that this inner square is a 1 by 1 square, then the distance between each of these red squares is 1 over square root of n. Okay, so let's assume that this size of sigma 0 is 1. Then I claim that one of these squares is a nice separator. Okay, let me try to show that. So we first want to show that I can pick one of these squares such that it intersects only square root of n of my disks. Okay, and well, if you take a disk like this one, okay, obviously the number of squares it intersects depends on its diameter. Right, and since these squares are a distance 1 over square root from each other, that means that the number of squares whose boundary is intersected by this disk is this number here. It's its diameter times square root of n. Right? If the diameter would be 1 over square root of n, okay, then it's essentially has the same size as the distance between two such things, and it intersects at most 1. If the diameter is 1, then it will intersect all of the squares. Okay. And so if you look at the disks that intersect, well, sorry, oops, let me move this a little bit. Okay, so if you look at the disk that we care about, then the sum of the areas of the disks is order 1. Okay, why is that? Well, this red square has, okay, it's a 3 by 3 square, so it has area 9. Each of these squares, we can assume it has constant area, because if it would be much bigger, there's only very few of them because the disks are disjoint. So these super big disks I just put into my separator and I ignore them from now on. So I only need to look at disks that have area at most order 1. And then, well, because they're disjoint, then all the disks intersecting this red square have total area order 1 actually. Okay, and if you combine these two things, then it's not hard to show that there must be one of the squares that intersects only square root of n disks. Okay, if you think about it, probably if you sit down for a couple of minutes, you will be able to do this computation. It's not very hard. Okay, intuitively, there are very few big disks that are intersected, and the small disks, they intersect only few squares, so you can avoid them. Now, the second thing is that, of course, I need this square to be balanced, meaning I do not want to have almost all squares inside, and I do not want to have almost all squares outside, sorry, disks inside, and I do not want to have almost all disks outside. Okay, but that actually holds for any of these red squares. Why is that? Well, remember that this small square in the middle contained at least n over 36 disks. So on the outside of any of my red squares, you can never have more than 35 over 36 times n disks, right? Because there's n over 36 inside. So you do not have more than a constant fraction outside. So what about inside? Well, the largest number of disks are inside this red square, right? Of all the red squares I've drawn here, this outermost one is sort of the most dangerous one. That one I can partition in 9 squares of the same size as this inner one. And so now I'm going to lie a little bit. That kind of implies, because this is the smallest square containing n over 36 disks, that each of these other guys cannot have more than n over 36 disks. Okay, so each of these things has only n over 36 disks. So in total, that's 9 over 36. So also inside, you don't have too many disks. Right now, you may wonder why n over 36?
Mark, did you mean each of the other square must contain at least n over 36?
No, at most. Right?
Where did you use the property that the middle one is the smallest square containing n over 36?
Okay, so this one is at most n over 36.
At least.
Okay, at
Oh,
least.
at most, okay.
Right, but it's the smallest one.
Right. Oh, yeah, okay, sorry.
Right?
Okay.
So maybe you also see why I'm lying a bit.
Because you ignore disks that are crossed by the boundaries of the...
Exactly. So that's also why there's this n over 36 here. Otherwise, I could have chosen n over 10 or something like that. So you have to play a little bit, and instead of these this 3 by 3, you make it a 6 by 6, and you ignore disks that are relatively large and so on. But that's, I mean, this is the basic idea, that because in here you don't have many disks, that means that inside this 3 by 3 one, you also cannot have too many disks.
Yeah.
Okay, so this is the idea of the proof. And yeah, if you see the details, it's actually not very hard. So now let me give two applications of this planar separator theorem. And the reason I'm giving these two is because later on we will see that also for these clique-based separators, you can do the same thing. So the first application I want to give is independent set. Okay, so I give you a graph and I want to compute a maximum independent set. Okay, this is NP hard. And in general graphs, actually, you cannot do this in sub-exponential time, meaning you cannot get anything of the form 2 to the little o of n, okay, if you assume the exponential time hypothesis. On planar graphs, however, you can do a lot better, namely 2 to the order square root of n. And that's actually also best possible if you believe the exponential time hypothesis. And the algorithm is trivial once you have a planar separator, because what you do is you compute this planar separator, and here I put 2/3 for the balancing factor, but that doesn't really matter. And then I simply try all possible independent sets for the separator. But I've square root of n nodes in my separator, so that's 2 to the square root of n different possible independent sets. Once I guess, or you could say I try an independent set here, I say, well, if this is in my independent set, then recursively I compute an independent set here, but if I already pick this one in the separator, then these two I should already remove from this side. And also from the other side, I do something similar, right? So I recursively find an independent set on this side for the nodes there minus the neighbor of the independent set I picked. I do the same thing on the other side. And then for this particular guess of my independent set on the separator, that's what I return. The independent set of the separator plus these two recursively computed independent sets. And then I simply pick the largest over all my guesses. And then obviously one of my guesses will be the actual guess. So this will give a maximum independent set. And the running time, okay, you have to compute this separator. Actually, you can do that in linear time in a planar graph. Then I have 2 to the square root of n number of separate independent sets in my separator. For each of them, I recurse. Okay, actually, I recurse twice, once on the left side, once on the right side. But that's, of course, subsumed in this 2 to the square root of n here. And then maybe I have some overhead term for, I don't know, picking the largest of the 2 to the square root of n things I find. And this solves to 2 to the order squared of n. Right, so this is a trivial algorithm that gives an optimal result for independent set on planar graphs if you insist on finding the actual maximum. Okay. Here's another very simple and basic application, distance oracles. So I give you a graph, possibly edge-weighted in general, and you want to pre-process it such that you can report the distance between any 2 query nodes. Okay. There's a very old and basic result, which has by now been improved many, many times. But the first and maybe most basic result is that for planar graphs, you can do this with order n root n storage and order root n query time. And again, if you have a planar separator, that's actually trivial to obtain, because what you do, well, you take your separator, you compute a balanced separator for your graph. Then for each node in your graph, you take the distance of that node to each of the points on my separator, right? So each node on my separator, I compute the distance from here, this node U, to this node, V in the separator, and then I recursively compute a distance oracle on the left and on the right. Okay. So now what do I do when I get a query? Well, I get as a query, let's say this node here. I compute, so as a query, I have 2 nodes, S and T. So I first compute the distance if I insist on going via the separator. So what is that distance? Well, it's the minimum over all nodes in the separator of the distance of S to that node plus the distance of T to that node. Okay, that is the best possible if you insist on going via the separator. And, well, of course, if S and T lie on opposite sides, you must go via the separator. Or if one of them is on the separator, you also go via the separator. So only if both are in, let's say, this part of the graph, or both are in this part of the graph, then you have a different option. So let's say both are in A, then I also compute the shortest path in the subgraph for A, right, using the distance oracle I have for that part, and I report the minimum of a path via the separator and a path that stays inside A. Okay, and for B, it's the same thing. And then you will see that you get query time is square root of n, right? Because here I spent square root of n time and then I recurse. And my storage is n root n. Okay, this is actually very naive. And by now, there's a much, much better bound for planar graphs that has near linear storage and almost an essentially logarithmic query time. So that's very, very nice. But almost all these improved algorithms for distance oracles, they somehow start with or also use some kind of separators.
Mark, question. So between 96 and 2023, there was no progress.
No, there were many developments. So this is a long sequence of papers that started in 96 and that eventually culminated in this 23 result. There was a result by Turup from, I don't know, 2005 or something, I forget, maybe even older. So it's a long sequence of papers that led to this thing. Okay, but yeah, again, this is very basic. Later we will do something like this for geometric intersection graphs, which is equally basic, but somehow gives a result that was in a setting where nothing was known. Right, so the main question is, for these distance oracles, can you do something with less than quadratic storage and less than linear query time? And in general, that's impossible. I mean, if, for instance, if you have, or if you want both, right? If I give you a bipartite graph that is almost complete and you forget about one edge, okay, then how are you going to know that the distance between them is 1? So yeah, for exact queries, there's not much you can do. But in planar graphs, there is a lot you can do, as you can see here. Anyway, let's get to the main topic for today, which are these clique-based separators. So yeah, I'm going to look at intersection graphs of objects. So let's say disks. So I give you a set of disks, and I put an edge between two disks if the disks intersect, right? So the nodes in my graph are the objects, and the edges represent intersections. So there's a number of nice examples. I can look at disk graphs, which have been studied quite a lot. Of course, you can also do disk graphs in different metrics, right? So here I can look in a simple polygon or a non-simple polygon if you want. I have a set of points. Each point I assign sort of a radius, and then I look at all the points at geodesic distance, that radius from the center, and then I get a nice graph like this. You can look at string graphs, right, where the nodes are strings, and you put an edge if the two strings intersect. You can look at map graphs. So map graphs are planar, a little bit like planar graphs, but not quite. So you take a planar subdivision, like you see here. You look at not just the dual, but you add an edge between any two regions if their boundaries intersect, and even if the boundaries just intersect in a single vertex. Right, so for instance, here you see this red vertex. You've all these regions around it that are touching in this vertex, so they form a clique. Okay, so this graph is not planar. And yeah, there's many other types of intersection graphs we could look at. And of course, these graphs do not have small separators, right? Because they can have arbitrarily large cliques, and if you have a large clique, there's no way you can have a small separator. But they do have what we call a nice clique-based separator. So here I also want a separator, right? I want to separate my graphs into two parts without edges between them. But instead of removing individual nodes, I remove cliques. And the size of my separator is counted in terms of the number of cliques. Okay, so you see the formal definition here. it's a collection of cliques, disjoint. If you remove the cliques, you get a nice balanced separator. And the size of this separator is not the total number of nodes in the cliques, but just the number of cliques. For some applications, as we will see, it's actually also not just important how many cliques you have, but also how big they are. And for that, you can define the weight of the separator as not the number of cliques, but you take the sum of the logarithm of the sizes of the cliques. Okay, so let's see. I guess this is, yeah.
Can you give us intuition for the weight, for the choice of weight?
You will see it in a minute.
Okay.
Actually, the result that I will give you also applies for larger weight, up to square root, essentially, of the size of the cliques. So you take the sum of the square roots. But in the applications that I know of, you work with a log, and we will see why. Okay, so, I mean, this is a nice definition, but you can wonder, do these things exist, and are they good for anything? So let me first sort of hand wave that they exist. And let me do that for disk graphs. Right, so any disk graph has a clique-based separator consisting of square root of n cliques. And actually, the total weight of these cliques is only square root of n. And the proof is actually exactly as before. Well, kind of exactly as before. So I also take this smallest square containing, let's say, n over 36 of my disks in its interior. And then remember what we sort of argued that, okay, disks of a certain size, if they're small, they don't intersect many of our candidate separator squares. Now what I want to do is I want to group these disks into cliques. And remember that kind of if you take a very small disk like this one, it's sort of relatively easy to avoid it by picking the right square. Okay, if I have a large disk, it's difficult, or it may even be impossible to avoid it with any of your squares. It used to be the case that these large disks, there were only very few of them, right? Because in the earlier setting, these disks were disjoint. Now the disks start to intersect, but if they're large, then they form very few cliques, right? You can stab them by a few points. So it used to be that I had only very few large disks to worry about. Now I have only very few large cliques, or cliques of large disks, I should say, to worry about. So the proof then goes, okay, now it becomes more technical, and not going to give the proof, but you separate the disks, distinguish different size classes. For each size class, you see how many points you need to stab them, and so on. And then if you're very careful, you can argue that the same proof kind of goes through. Okay, so with this, you get a separator consisting of square root of n cliques, and actually their total weight is even square root of n. So now let me show you two applications, and the first you will see why the weight and the comes up and why this is chosen as the log. So let's look at independent set, and I claim that with exactly the same algorithm as before, I can now solve independent set in optimal time, right? 2 to the order squared of n, or I should say optimal under ETH. So I do exactly the same thing. The only difference is that my separator is now a clique-based separator. And for the rest, I do exactly the same thing. Right? I pick all possible independent sets in my separator. Right? These are again independent sets of individual nodes. Once I guessed my independent set, I recurse on the two halves. Okay, so the nice thing is that it used to be that the separator had size squared of n. That was the number of nodes, and therefore you can pick an independent set in that separator in only 2 to the square of n number of ways. Now, of course, the number of nodes in my separator can be very, very large, but from each clique you can pick only one node, right? Because you are picking an independent set. So what is the total number of independent sets I have to try inside my separator? Well, at most one node from every clique. Okay, so I pick either one node or 0 nodes. So the total number of choices for one clique is the size of the clique plus 1. Right, I can pick every node, so that's this many choices, or no node at all, that's the plus 1. Then all combinations, well, I have to multiply each of these choices for each of the different cliques. And then, okay, the product of these numbers is 2 to the sum of the logarithm of these sizes. And that's where the log comes in. And we know that this sum was the weight of the clique of the separator, so that's 2 to the square of n. Okay, so that's nice. Distance oracles. So again, we do exactly the same thing as before. So if I want to have a distance oracle for disk graphs, then, okay, I compute a clique-based separator. But now I used to compute or pre-compute for each node the distance to any of the nodes in my separator. Right, and that was okay since the separator only had squared of n nodes. Now the separator has many nodes, but only squared of n cliques. So instead of computing for this node the distance to each of the nodes here, I compute the distance to each of the cliques. Right, so that's what you see here. For every node U and every clique Ci, I compute the distance, right? So the shortest distance to any node in the clique. Okay, and then I recursively compute distance oracles on the left side and on the right side. Okay. Query algorithm is exactly the same thing, right? I compute the distance via the separator. And then, okay, if things are on different sides, then that's my answer. Otherwise, if both nodes are on this side, I also compute recursively or using my distance oracle for this part of the graph, I compute the shortest distance that does not visit the separator, and I report the best of the two. Right? And this distance via the separator, now I make a small, possibly make a small error, of course, because if I go, let's say, from here to, I don't know, here, via this separator, okay, I go to the separator, and then from the separator, I sort of continue on the other side. but I'm not sure if from here and from here, I go to the same node in this clique. So I might be off by 1, right? But not more than that. So I get an almost exact distance oracle with en-root end storage and square root of n query time. And somehow surprisingly, this is new. And for non-planar graphs, there were only distance oracles with subquadratic storage that had a multiplicative error of, let's say, 2 or maybe 1 per epsilon or something, but something that is almost exact was not known. Even for
Mark,
yeah,
don't you accumulate an error of 1 at each recursive level?
no, because if you look at the recursion here, that is a recursive call where you do not go via nodes in the separator. You stay completely in this side, right? So you get a result from the recursive call, which is an exact result up to an additive error of 1 for all the paths that stay completely inside here. And for this guy, you get the optimal result up to an additive error of 1 of all the paths that somehow go via something in the separator. Right? Because there's no plus here, but a min, it doesn't accumulate. Right? And that also, that kind of makes it hard if you now want to improve on the storage by doing something different in a recursive fashion. Then you might start up accumulating errors maybe, but because here I simply compute for every node here the exact distance to each of the cliques. And for every node here, the exact distance to each of the cliques. The only mistake I made is inside this clique, which is a mistake of 1. Okay. Yeah. So let's continue. If you have such a clique-based separator, there's many other things you can do. So here, suppose you have a graph class where you have a separator of size Sn, right? Which is now the number of cliques. And the weight of such a clique-based separator is Wn, right? That's defined as here. Then, okay, like I said, I can do independent set in 2 to the weight of the separator. I can do feedback vertex set, same thing. I can do coloring. I can have this approximate distance oracle. I can do dominating set and Steiner tree under certain conditions. I have this, okay. And there's some more results that use these kind of separators. So, okay, I hope I convinced you that the separators are somewhat useful. I have shown you how to compute them for disks. Now let's see if we can also compute them for other objects. And here you see an overview of the results. Right? So for disks, we get square root of n size and also square root of n weight, which is optimal. Fat convex objects, you get the same thing. Map graphs, okay, we can also do the same thing. I will show you, or hand wave in a minute. Geodesic disks inside a simple polygon and pseudo disks, there we don't know what the right answer is. I believe it should be square root of n, but yeah, I don't know. I used to be fully convinced. Now I'm semi-convinced, but I'm not really sure. If you have pseudodisks that are polygonal with n vertices in total, then again, I get to square root of n. Yeah, the weight has a log more. For geodesic disks, in a very general setting, you get n to the 3/4. And so what I'm going to do in the rest of the talk, how much time do I still have, Danny?
You have 10 minutes still, and then questions.
Okay, 10 minutes. Okay, so I'll let me see what I can do. Yeah, and there also in higher dimensions, there's also some nice bounds. So let me try to hand wave a few of the results because they use different techniques to compute the separator than what we've seen so far. Right, so how do we construct these things? Fat objects and disks we have seen. Right, essentially the proof I sort of sketched a little bit for disks. If these objects are fat, it works in the same way. Right, the thing is that because they're fat, if they're large, you can also stab them with few points and so on. So this we sort of know how to do. Map graphs. Okay, let me give you a different construction for map graphs. So here you see a gray subdivision, right? So the nodes are these regions. And instead of drawing the map graph, I've drawn here a witness graph, which has a node for every region. Those are the blue nodes. But I also have these red nodes that are sort of witnesses for when two regions intersect. Right? So here, these two regions intersect, and I actually have two witnesses. Here, I can go via this red node or here. And for instance, this red node here serves as a witness for the fact that all its blue neighbors form a clique. Okay, so if two blue nodes are neighbors in my map graph, then I will have a red node such that I have a path of length 2 between these two blue nodes via this witness, this red witness. But then you can just here, yeah, you can put them on vertices or edges or whatever. You can do this in such a way that this is planar, which is not difficult to see. Okay, so now what I can do is I had this map graph which is not planar. Instead, I look at this witness graph that is planar and still has linear complexity. I compute a separator in this witness graph. And whenever my separator puts a red node, whenever my algorithm puts a red node into the separator, I simply put all the adjacent blue nodes, which is fine because it's a clique. Okay, so that's easy. I get a separator of square root of n cliques, and the weight of a clique is never more than log n, so the weight is square root of n times log n. Can we do better? Yes, there's a nice trick where if you replace each of these witness nodes by this little gadget, right? So it used to be that this was a star centered at this thing, and now I have some planar gadget here. Oops, and that essentially says, okay, if I want to separate, okay, intuitively you could say if I want to use, if I now apply my planar separator theorem, and it wants to separate things here, if it wants to separate a lot of things, it has to go deep into this gadget, and going all the way to the central node is going to take you the log of the number of leaves of this gadget. And so that's why now putting this clique into the separator, if you look at the planar separator that you get, it will cost you log n, because you have to go all the way to the center of this thing. And that's, I was allowed to pay the log. I mean, that's the weight in my separator, in my clique-based separator. So that's kind of the idea. Okay, two more techniques. So if you have pseudo disks, then there's a separator of size n to the 2/3. If the pseudo disks are polygonal, then there's a separator of size square root of total number of vertices of these pseudo disks. And yeah, what you do is you first find a small set of points that stabs all the pairwise intersections. Okay, so if you're lucky, then with one point you can maybe stab many disks at the same time, many pseudo disks at the same time, and then you capture lots of pairwise intersections. But yeah, if you're unlucky, that maybe you cannot do. And then you compute what is called a planar support of the hypergraph on these points. So these red points stab all the pairwise intersections, right? So whenever two pseudodisks intersect, I have a red point in their intersection. Then I can look at a hypergraph where these red points are the nodes. And if I look at this, each pseudodisk, like this one, that defines a hyperedge, right? So there's a hyperedge with this point, this point, this point. There's a hyperedge here with this point, this point, this point. Okay, so I have this hypergraph. And this blue thing is a planar support. So what's a planar support? It's a planar graph on these red nodes, such that the following holds. Whenever I look at a hyperedge, okay, so let's look at this hyperedge. It has 3 nodes. If I now look at the subgraph of my planar support induced by these 3 nodes, that should be connected. Right? So indeed, if I look at the graph here, 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 it's connected. If I look at this hyperedge, it has 2 nodes and there's an edge between them. If I look at this hyperedge, I have this node, this node, this node, this node. Oh, so I see I made a mistake in my planar support because that's not connected, right? I had these 2 and these 2, but there should have been an edge here as well. Otherwise, the subgraph induced by these 4 things is not connected. Okay, so you have this planar support, and then what the general strategy is, you try to find a planar support with a small number of nodes. You compute a separator for this planar support, right? It's a planar graph. So that has square root of n number of nodes. And then for each of the red nodes in your separator, you compute or you put all the pseudodisks that contain this node as a clique into your separator. Okay, so compute this blue graph, it's planar, compute a separator. Whenever this point is in my separator, oh, I look at it is inside this, this, and this thing, so let me put it as a clique into my actual separator. My separator for the intersection graph. So if you do this, it turns out that it is a separator, so it really separates. And yeah, the size of the separator depends on the size of the planar support. If my pseudodisks are polygonal, I can find a small planar support, namely with only linear number of nodes. If the pseudodisks are not polygonal, then we don't know of any planar support that has linear size, and the planar support will have something like n to the 4/3 nodes. And therefore, the separator will have n to the 2/3 nodes.
How do you prove the n to the 4/3 support?
Yeah, that's kind of very naive. You simply okay, so you remove all cliques of size more than n to the 1/3 or 2/3. Okay, those you simply put into your separator, right? So cliques of size n to the 1/3, you don't have more than n to the 2/3 of them. So you put them into your separator. After that, you have an arrangement whose depth, whose ply is n to the 2/3, sorry, n to the 1/3. And therefore the whole arrangement has n to the 4/3 complexity, and then it's easy. So it's a very naive way of doing it.
So that should work also for what is called the non-piercing region, which is more general than pseudo.
Yes, I guess so, yeah.
It's all separate. Okay.
Okay. Now the most recent thing for which I do not have time, because I see our chair getting very nervous, but let me explain the result, because I think the result is actually quite nice. So this is a very, very general setting. So you look at essentially any kind of distance, any kind of metric defined on the plane that you can think of. So, okay, take a polygon with holes, look at geodesic distances, take regions with weight and look at the, the length of a path. You multiply each of the parts with the weights of the region you go through, or you take a polyhedral terrain and you move on the terrain, right? It's also if you project some kind of distance, some kind of metric in 2D. For any of these things, there exists a clique-based separator of sublinear size, n to the 3/4 actually. The result is using this result on string graphs, namely that any string graph has a separator, a normal separator, right? I kind of nodes, not cliques, where this number of nodes in your separator is the square root of the number of edges. Okay, so if you have a quadratic number of edges, this is useless. So the strategy is to somehow try to get to a situation where you have a sub-quadratic number of edges. And yeah, there's a very nice way of doing that, for which I don't have time to explain it, but let me rush in 2 minutes and hand wave if that's all right with you, Danny.
Sure.
Okay. So first, I want to have a set of objects where the ply is small. So as soon as I have something that is where the ply is high, it's a clique, I remove it. I have something else where the ply is high, it's a clique, I remove it. Okay, so now the ply of my system is small. Now I want to prove that the number of edges is small. Okay. And then once I've proven that the number of edges is small, I can get something from the separator result on string graphs. So how do I prove that the number of edges is subquadratic? Draw the graph in the following way. You pick the centers of your geodesic disks as nodes, and you connect two nodes via a shortest path. Okay, so, and then you start looking at the crossings between these shortest paths. And okay, the idea is that if you have many edges, then by the crossing lemma, you have many crossings. But if you have many crossings, then we show that one of these crossings must have high ply. And the reason is something like this. So if I have a crossing here, okay, this is the shortest path, and this is the shortest path. Okay, so if, let's say, this is longer than this, then this portion is completely contained in this geodesic disk. Okay, but that means that all the other crossings that are located on there, they're all inside this geodesic disk. And so you can imagine that if you have many crossings, that somehow you can argue that you get also many crossings inside many disks. So the total ply over all the crossings is large, and therefore there is one crossing that has very large ply, but that's not possible because we started by removing things of very high ply, so the ply was low. So that's very hand-wavy and very fast, and I realized too fast how the proof works. And then you need to do some more work if you want to get to n to the 3/4. Okay, so this is a short summary of the results. Right, so here again, I've put all the objects for which I know that there is a sublinear clique-based separator. The gray bounds are not optimal, so I invite all of you to improve them and let me know when you have done so. Other nice questions, I think, is if you look at this distance oracle, okay, it gave a new result for even for disk graphs, but it was very naive what we did and very simple. So the hope is that maybe if you try to do similar improvements that were used for planar graphs, maybe you can apply similar techniques here and also get improved bounds on distance oracles for intersection graphs. And yeah, I already gave a large number of applications, but I think that there will be more things where you can use clique-based separators. And this is it. So thanks for listening.